So, Gary, are you there? Can you take from here?
Yes, I am here. I am in quarantine in rainy Toronto. So I
Good.
will start off
Yep.
with, have I shared?
Yep. I think you can share. There should be.
There we go. Can you see it?
It's
Or
coming.
is it coming? Yeah, good.
Yep. Now we can see it. Yep. We are in the.
Great. Okay, and let's get up to the start. Sorry about that.
Yep.
There, you've seen it backwards. Now I'll show it to you forwards. I'm going to talk about, one of the central problems of designing the breeding pipelines, and that's the definition of the target population of environments, your breeding target. And I'm going to do that within the context of selection theory. The decisions you make around designing a TPE should be made in order to maximize genetic gain. And there's a body of theory and modeling approaches that allow you to analyze your breeding program in that way. This concept of the TPE was first, you first find it in print, I think, although it's an old concept in a paper by Cooper and Bith in 1996, which is, it's really the set of fields in future seasons in which the cultivars you're developing will be grown by farmers. So you can define the TPE as a geographical unit, state, region, a season, wet versus dry within a geographical area, a management system. High versus low fertilizer use is often very important in sub-Saharan Africa. A group of fields that have similar soil or hydrological conditions leading to similar types of stresses. The key feature of how you define your TPE is you have to be able to put a location into that TPE before you plant, right? You have to be able to say, okay, I know this field should be in this TPE. The stress feature that's causing G by E it can't be predicted before you plant at all, then you can't really use it to help you define or delineate the TPE. Clearly defining the TPE is really a key step in breeding pipeline design. It informs all decisions about testing. Decisions like where should trials be located, how many trials should be conducted, and when should they be conducted? Should they be planted early or late in the wet season, the dry season? How should they be managed agronomically, high versus low input? And it's important to realize that your trials are not the TPE. Your trials are selection environments that are meant to represent the TPE of farmers' fields in future seasons. You use them for prediction. And that means that really breeding, testing is an exercise in indirect selection. Your purpose of testing in the selection environment, say in the trials you're conducting in 2021 on the research stations in your testing network, is really to predict performance in farmers' fields a few years down the road. Really, the one place in the TPE farmers are not going to grow your varieties is on your research station, right? So research station trials are really for prediction, and therefore it's really important to understand the genetic correlation between performance in the selection environment over here on the left and performance in the target population of environments. We can't currently at least do a very large amount of on-farm testing. So we do have to use research stations as a proxy for performance on farms. But going forward, I think in CG breeding programs, and in our breeding networks with partners, we really have to think about how do we push more of our testing on farm. And the foundation will be supporting efforts in that direction. One thing that's important to recognize about some CG programs is some of them, like the Simmet wheat program or the Erie irrigated rice program, do a huge amount of their selection, apply about 95% of their selection pressure far outside the TPE. So the Erie rice program does a lot of its selection at Los Baños in the Philippines for performance in regions like South Asia. The Simmet wheat program does a huge amount of its selection at Obregon in order to predict performance on farms in South Asia. So it's absolutely a professional responsibility of plant breeders managing programs like this for us to really estimate the genetic correlation between performance in our trials in the selection environment and performance in the TPE, and to track that. It can change over time as management practices change, environment's changing as well. There's a body of theory, pretty old, that allows you to predict correlated response in the TPE to selection in the selection environment. It's just the standard, modification of the breeder's equation to explain correlated response to selection. So correlated response in the TPE to selection in a selection environment is a function of selection intensity in the selection environment, the genetic correlation between the selection environment and the TPE, heritability in the selection environment or repeatability, and genetic variance in the selection environment. So this, this allows you to think about how to maximize that correlated response. And all of these parameters can and should be estimated. Even when you have a well-defined, well-designed TPE, there's still genotype by environment interaction within it. And so the question remains how to deal with that G by E. So there's two types of G by E that occur within a TPE. One is basically recurring or fixed factors that only are apparent after planting. For example, after you planted a tree, you don't know if you're going to have a drought or a flood at a location before you plant, but you do usually know the likelihood of a drought or a flood at that location. So you know the frequency of those types of stresses. So that type of G by E can be managed by weighting. You're going to have a certain frequency of drought trials in the testing process. You're likely to have a certain frequency of flooded trials, for example. So you can assign weights to those trials, or you can report the BLUPs out of droughted trials versus non-droughted trials separately in your report, and then select genotypes that do relatively well in both. Those are really the options that you have available. The other type of G by E that you have, you can't develop separate cultivars for the droughted trials versus the non-droughted trials, because drought occurs relatively randomly at different frequencies within the TPE. So it's important to understand that once you've defined your TPE, that's your target. You're not going to develop varieties for little subsections of your TPE. If that's the case, you really need to divide the TPE. And we'll talk about that in a minute. There's also random environmental variation that's simply noise among, in the way cultivar means bounce around from location to location, field to field, year to year. There's nothing you can do about that except replicate. It's just noise. It's like plot error. So you have to have enough locations within the TPE to deal with that type of noise. An example of predicted frequencies of stress environments, for maize within, say, Eastern Africa, might be that 50% of trials, maize trials in that the CIMMYT maize program runs have some drought during grain filling. 20% have no drought at all. 30% might have flowering stage drought. I mean, these are made up numbers, made up frequencies. They don't represent actual frequencies. But then, if you know this, you can assign weights relative to the frequency of these types of stresses in making a selection decision. If you think you have a fixed factor that really you can predict before planting and probably results in a lot of rank change among your selections, it may be worthwhile to divide your TPE into sets of more homogeneous sites. If you have a pre-existing hypothesis about geography, soil type, management system, you think, well, I think I need to develop different cultivars for high fertility versus low fertility management, different types of farmers, then you can incorporate that factor into an analysis of previously run trials to test the hypothesis. You can put it into the model as a fixed factor. If you don't have and usually you should have a pre-existing hypothesis about how and why you want to divide your TPE. If there's no pre-existing hypothesis, but you just think there's too much G by E and you want to understand how it works, you could do some type of cluster or pattern analysis biplot to come up with a hypothesis about how different types of environment within the TPE, but it would just be a hypothesis. One of the problems with cluster analysis type approaches is that they often don't repeat when you look at a later another series of years or trials. If you have to remember, though, that if you decide to divide your TPE, you also invariably divide testing resources. And this has the potential, actually, it will certainly reduce heritability within the new subdivided breeding targets. So let's say you have a TPE, your original region here, and you can afford to run 6 trials every year within that region at 6 locations, and you think maybe we need to divide that into eastern and western zones. Well, obviously, unless your boss says, well, I'll give you another 6 trials so you can have 6 in each subregion, you're going to reduce your testing resources within each subregion. So this has the potential to reduce heritability, doesn't it? And so you before you make that decision, you really have to justify it. And how do you justify it? You justify it, well, in terms of, you assume there's a low genetic correlation between these 2 subregions, and that subdividing will allow you to increase the rate of genetic gain that you deliver within each subregion. And this can be modeled, and you can come up with a prediction for whether you should do this or not. The genotype by subregion model that you can use to test the hypothesis as to whether you really need those separate programs for those subregions, is an extension of the standard model for analyzing multi-location trials. This is a simple version that just looks at locations within a year or environments. But you can extend it to a trial series conducted over years and locations. That describes the yield of a plot as the mean of all the whole series plus a location effect, a rep within location effect, a genotype effect, genotype by location effect, and plot error. And if you want to split, if you're assuming that you'll explain a lot of G by E by subdividing your target population environment, what you're really saying is that we're going to have 2 groups of locations. We're going to divide our locations into subregions, say 2 or more, and then we're going to have locations within each subregion. So you split, you put in a subregion factor, and you're left with locations within subregions. And any G by E term that has locations in it also needs to be separated into a genotype by subregion, genotype by location within subregion term. Subregions, this S term in this model, they're fixed. You know about them in advance. You want to make inferences about them. Trials within subregions are assumed to be a random sample of that new TPE. I can't see my bottom. Yeah, if genotype by subregion interaction term is not significant, subdivision is unnecessary and could be harmful because you're reducing testing resources. If it's significant and large, you may get a benefit in terms of heritability. There we go. What really happens to heritability and genetic and G by E variances when you subdivide and start set up two separate programs for one for each region? Well, in the whole region, heritability is the ratio of the genetic variance for the whole region to the phenotypic variance, which is as a genetic variance, genotype by location variance divided by the number of locations in the whole region, and the error variance. What you're doing when you subdivide is you take that genotype by location variance and you divide it into a genotype by subregion term and a genotype by location within subregions, with fewer locations now represented by that L apostrophe. And oops. Am I sharing still?
Yes.
Okay, sorry, I messed around there for a second. What happens when you subdivide is you move that genotype by subregion variance, you add it to the genetic variance, and you take it away from the genotype by location variance. So you're moving some G by E into the genetic variance term. So this could, if genotype by subregion interaction is big, that could increase heritability. But if it's small, it'll reduce it because you reduce the number of locations effectively that you have to test with. So this gives us a guide to how we to how to decide whether to divide a TPE or not. We should subdivide it if and only if this will result in higher genetic gains within each region. It increases subdivision, increases genetic variance within each subregion by turning some of the G by E interaction into genetic variance. That could increase heritability, but it also reduces the number of trials available for testing within each subregion, and this could reduce heritability. So the key question is, does the increase in genetic variance resulting from subdivision outweigh the decrease in heritability from fewer trials within the subregions? And there's a pretty straightforward modeling approach to assessing that. It's the formula for estimating the magnitude of correlated response to direct response, and you can apply this to the correlated response in each subregion to selection in the undivided region as a whole. Are you going to make greater gains if you don't subdivide than if you select within the subregions? And that's a function of the genetic correlation between means estimated in the whole undivided region and the means estimated in the subregions, multiplied by the geometric mean of heritability in the whole region with all the locations considered versus heritability within the subregion with the subdivided number of locations. And these, there's ways to estimate all these components. You'll see an example, I think, of this from Christian in a few minutes. You can calculate that genetic correlation between the whole means estimated in the whole region versus means estimated in the subregion directly. There's a method originally published, I think, by Mark Cooper, which estimates this type of genetic correlation as You get the phenotypic correlation between means in the whole and the subregion, and you divide it by the geometric mean of the heritabilities. That's, it tends to be very sensitive to variance component estimates, so you can get, it tends to be a noisy estimator. You can also estimate it as an intra-class correlation coefficient. This is the formula for that. It's a function of the genetic variance across the whole region, and the genetic variance across the whole region times the genetic variance within each subregion after you've subdivided. Both are relatively easy to estimate. This one doesn't work if you would have a negative genetic correlation between subregions, and it's also quite sensitive to differences in genetic variance size within the subregion. So there are advantages and disadvantages to all of these types of estimator, and sometimes you want to look at both and make sure that they agree with each other. Quick example, this is from an analysis that was conducted by Vanessa Windhausen, published in Crop Science in 2012 for her PhD at CIMMYT. She tested the hypothesis as to whether Eastern and Southern Africa should be treated as separate TPEs by the CIMMYT Maize program. She looked at 275 stage 3 yield trials from 2001 to 2009, large number of hybrids and trials. And she found that, separate analyses for early maturity group and late maturity group hybrids. And she found that genotype by subregion interaction explained very little of the genetic variant of the G by E variants for both the early and the late maturity group. And so you really would not, in this case, see any benefit from subdividing in terms of selection for yield. There might be other reasons to subdivide the TPE, different quality requirements. I don't think that's really the case in this case either, or different disease resistance is required. But in terms of selection for yield, there's really no reason, according to this analysis, to be subdividing, operating completely separate breeding pipelines for Eastern and Southern Africa. So that's the that's the application of the fixed subregion model to deciding whether to subdivide or not. Are some locations, so questions that people have often you hear about are some locations more representative than others in a TPE? Can we drop unrepresentative locations to reduce cost? If you've designed your TPE properly in your testing system, locations are just replicates. They're just samples of environments in the TPE. They should all be representative. You don't normally decide whether how many replicates you want in a field trial by deciding whether a replicate is representative or not. You decide how many reps you can afford, and you run that number of reps. It's the same with locations. Unless you really have evidence that one location is consistently not correlated with the others, you should include them. And the best way to decide whether to include a location or not is whether including it increases heritability or decreases heritability from the combined analysis. And I'm just trying to get a bar off here. Often people wonder whether they need to do a lot of testing of finished products to figure out where they should be grown within a TPE. Well, if your breeding pipeline is serving the whole TPE, you shouldn't have a lot of specific adaptation to the little niches within the TPE. That means your TPE isn't well defined. So The purpose of late stage testing is not to find out where a variety is adapted. You bred it for the TPE, it should be adapted to the TPE. It's simply to determine whether you were correct, whether the proposed product is really superior over a range of seasons and fields to what farmers are currently growing. All right, why can't I advance? There we go. So in conclusion, designing the TPE is one of the most important steps in breeding pipeline design. TPE should be delineated in order to maximize genetic gain. And to do that, you need to use a correlated response model. You need to understand the genetic correlation and the heritabilities within each of your proposed subregions. Often breeding programs tend to subdivide TPE too finely with no effort to determine really whether that subdivision is going to increase the rate of genetic gain. There is a body of theory that exists to help you determine whether to subdivide or not. And breeding programs that really select far outside the TPE in a centralized location need to understand the genetic correlation between that selection environment and the TPE. That's it for my overview. There's some references here on these methods that are pretty easy to get. If you can't, if they're not freely available, happy to share them. Thanks a lot.
Yeah, thanks, Gary. Please keep your questions for a couple more minutes. We would like to also have Christian Werner, analyzing, showing the analysis and results for some data set, which is related to the method that Gary just explained. So Christian, can you take from here?
Of course, thanks, Eduardo. Hi, everyone. Let me quickly share my screen.
Yep, thanks. Yes, we can see your screen.
Okay, excellent.
We just need to go to mode.
Yeah.
Great. Yep.
Okay. Again, welcome everyone. Thanks, Gary, for your presentation. So Gary now laid the foundation and that body of theory for this concept of thinking in terms of selection response about target populations of environments, which I think is a great approach. It's relatively easy to apply. You saw a couple of equations that Gary showed you, and it's hard to get around these equations when we have to model and analyze the data. But I will try to give you a brief example on TPE delineation, and I will try to avoid most of the equations, keep it as simple as possible, and show you using the CIMMYT's African maize program dataset to show you how to analyze the data and what we can get from this data, what we can learn from it when we analyzed it. Bit unconventional, but here I'd like to start with the acknowledgements, actually. So I need to thank Jill Cairns that she provided the CIMMYT African maize program dataset, and of course also need to thank Vivek and Joseph, Prasanna, and the whole maize team that we had access to this dataset. That was a bit of a last minute thing. We got access about 2 or 3 weeks ago, and then I also have to thank Eduardo and Gary. We constantly had discussions about how to model it. Eduardo and I had almost daily discussions about the modeling and shared scripts on a daily basis to get that done. So I'm going to talk about the data per se a bit. I don't want to present any data analysis without giving you a rough idea of what the data looks like, a bit about the modeling, but mainly about what the results are in this data set that we found and what we can learn from them. And I will focus on a subset of this maze program data set here. So I will not claim that this is a detailed analysis and that this is everything we need to draw conclusions, but I think it's a nice example to, again, make a point and show how Gary's approach can be used and can be useful to delineate plant breeding program TPEs. So the data set roughly looks like that. 227 maize hybrids were measured across 5 defined mega environments and across 6 years from 2013 to 2018. We had these numbers of plots across the 6 years in total. So it's with regard to the number of plots, almost balanced. There's a couple of few plots. There's a little few plots in 2015, but we get sufficient data across all years. What you can see here is the number of individuals tested in either 1, 2, 3, or even across 6 years. So we got 4 individuals which were tested across all 6 years, which give us some connectivity of the years. And these hybrids were tested in 5 mega environments. You can see those here, the colors are matched. So we have dry lowland, dry mid-altitude, wet lower mid-altitude, wet lowland, and a wet upper mid-altitude mega environment. And what you can see here is that most of the plots, almost half of the plots that were tested in the wet upper mid-altitude environment. The numbers you see here refer to the subset of hybrids of those 227 hybrids that were tested. So almost all hybrids were tested in all 5 mega environments. These mega environments consisted of 40 locations across 8 different countries. Most experiments were conducted in Zimbabwe. We had a total of a bit more than 16,000 records on grain yield, and these records came from stage 4. We focused on the optimal management subset of these of the data set, which means they were fertilized, there was no severe drought, there was no striga. And because we're in stage 4, selection for disease resistance had happened already before. So disease pressure was not really a big issue here. Now, as Gary mentioned, if you want to test your TPE, if your TPE is well designed, if you need to split your TPE, you need to start with a hypothesis. And the simple hypothesis we started here with was to check if we need a split into different mega environments, or if we could combine all mega environments, or if we could at least combine some of these mega environments to bigger target populations of environments. And Gary mentioned this key equation here to figure out if combining or splitting makes sense. We want to compare correlated response to selection to direct response to selection. So one example, let's look at wet lowland. Direct response to selection in wet lowland would mean the selection response that we can expect in wet lowland using genotypes that were tested only in wet lowland. So our genotypes would be tested only in the orange regions here. The correlated response that we want to compare to this direct response would be the selection response in wet lowland, so in these orange regions, based on genotypes that are tested across all of these mega environments. So we want to share and extract information from other environments, and that only makes sense if the information we get from these environments is useful. So this becomes a trade-off between as Gary said, the testing resources. How much can we test within wet lowland? How much can we test in the complete set of regions? And the trade-off between the testing resources and the sub-region specificity to represent the TPE we're interested in. So to do that, to compare that, we of course have to do a bit of modeling. I don't want to go into the details here. What is important is we need to estimate the heritabilities and the genetic correlations between our 5 target populations or our 5 subregions in order to compare correlated to direct response. We basically use the breeder's equation to predict correlated response, to predict direct response. And because a couple of terms cancel out, this is everything that remains, and we only need the genetic correlations between those subregions and the heritability of the whole or within the entire region and the heritability within the subregion we're looking at based on the number of the amount of testing resources we got. So in our model, we get a couple of terms. We get the subregion, we get the year effect, we get the location, we get the replication, and we get the genotype and a couple of interactions. It's not important to look in detail at that model, but I want to show you what in essence we're doing here. So we're defining the mega environment as a fixed effect, as a reoccurring effect. As Gary mentioned, we're not sampling here. We have a hypothesis that these mega environments are different. We're sampling locations within these mega environments, but we're defining these mega environments as a fixed factor. And this is also important when it comes to modeling the genetic correlations between these 5 mega environments. It's important that they're defined as a fixed factor. Now, within these mega environments, we got years, locations, replicates, which have an effect on the phenotype, which are not G/E interaction, which are environmental effects. So these are effects of the years, the location, and the replication, basically experimental design factors within these mega environments. So these are random effects. These are sampled. Now we're coming to the two important terms or groups of terms that were described before. What we do have here is our interaction between the genotypes and the mega environment. And what we want to get from this term here is the fixed factor that is repeatable. And we want to extract the genetic variances within those 5 mega environments and the genetic covariances between these mega environments. This is what we need to calculate the genetic correlations. This is what we need to calculate the heritabilities within the subregions. And then we have that noise G/E interaction component. These factors, these G/E factors, which we cannot really control, which change on a yearly basis, which are uncontrollable, at least to some extent, and which are therefore, again, a sampling effect, a random noise effect. We modeled, Werner and I modeled this component, the genotype by subregion effect using an FA model, factor analytic model. And this is a bit more complicated than the basic theory that Gary provided, but it allows a bit more flexibility. And what you need to know, everything you need to know here is that we can use a factor analytic model to approximate an unstructured model, which again gives us location-specific or subregion-specific genetic variances and specific genetic covariances, and therefore genetic correlations between all pairwise subregions. And now we just ran our model and checked what we see. So the factor analytic model gave us these genetic correlations between the different subregions, the 5 subregions. And you can see that they're, in general, they're pretty high. As we said, we excluded the random noise, and the fixed component that is responsible for G/E interaction is actually is pretty well controlled. We see that there's really high genetic correlations between the optimal trials conducted in the different 5 subregions. We also calculated the broad sense heritabilities, or repeatabilities, as you might call them. For the whole region, we of course got the highest because they're the most testing resources. And then you can see, based on majorly the testing resources that were used in the different subregions, that there's also different heritabilities. This is where half of the plots were grown. The wet upper mid altitude mega environment with most of the testing resources, and you can see that this heritability comes pretty close to the whole region heritabilities. Now, this is everything we need. We got our genetic correlations here, we got our whole region and specific region heritabilities, and we just put it in this equation here to get our ratio between correlated and direct response. Now, these are the values we got. And what you basically can see in 4 of these mega environments, the correlated response using the resources of the whole set of mega environments is higher than the direct response to selection in only the specific subregion. So this at first tells us here that, at least when we look at the optimally managed trials, that there's no really a benefit of only breed and only select within subpopulations. Actually, we make more gain when we use all resources that we have available, just because we have really high genetic correlations here, and we can use the information that comes from other environments really well. The only exception is the wet upper mid altitude environment. And this at first sight might be surprising, because when we look at the wet upper mid altitude, we see that it has really high genetic correlations with the other environments. But as I mentioned before, the heritability is already pretty high. And the information we extract from the other environments seems to be not that useful, given that the genetic correlations are not perfect. Again, within the wet upper mid altitude, there was a huge number of plots conducted. So we have taken a really big sample of plots within this mega environment, and we got a really representative set with a high heritability. Now, taking the other information into account would, as you see here, would not, if you compare these 2 heritabilities, would not massively increase the repeatability. And the trade-off apparently shows here that the genetic correlations with these other environments are not high enough to make extra benefit here. Now, does that mean we should split these environments? I would say no in this case, because if we split them, we cannot make use of this information that we get from these highly tested environment within these other environments. Thank you for unmuting. So if you split them, you obviously would make a little, just a tiny bit more genetic gain in this environment, but you would lose all the information that you get from this environment that goes in the other ones. So the second thing that was interesting is that dry mid-altitude, although these genetic correlations are still quite reasonable, they were a bit lower than those between all the other environments. And the major reason is, and that's what Jill told me, that many of the environments, the testing environments in the dry mid-altitude mega environment are located in southern Africa. And especially day length plays a role here. Day length is very different from the other environment, and therefore the genetic correlations are not as higher than the other environments. However, it still pays off to include the information from the other environments. It would not make sense to make it a single mega environment because the testing resources would be limited and we would make less direct response. A question is probably, why are the genetic correlations so high? And I said at the beginning that we looked at a rather limited data set or a subset of the original data set for illustration purposes. So we only looked at the optimal management. We had other factors in there. There were plots or whole trials which suffered from drought. There were low nitrogen trials. They were random stress trials, and we excluded them for illustration purposes. In a real data set, in real life, you could exclude them. But what we see is that if trials within these many different mega environments are optimally managed, we have a really high genetic correlation. Again, it was stage 4 material, so disease pressure might be different in the mega environments, but it didn't play a role here because we had made selection already for disease resistance, and regardless of the disease pressure, our material was relatively stable. And under optimal management, the major, at least detectable environmental differences were temperature, day length. I mentioned disease pressure already, and these had an effect, but apparently the effect was not strong enough to justify a subdivision into more environments. So I would like to conclude with this slide, which already becomes a bit more complicated, which is a factor, is the result of the factor analytic model. And what we see here is the percent of the total variation explained by the first two factor analytic model factors that we calculated. You can think of it a bit like a principal component analysis, and it tells you how much of the total variation is explained by the first and by the second factor. And the genotypes within these environments react to it with a certain sensitivity. So if there's only one single factor and they react to this factor with a certain sensitivity, this is only a scaling. There is no crossover genotype by environment interaction captured in this factor. It's only scaling. And this is very interesting because what we see here now is that most of the genotype by environment, by the fixed genotype by environment interaction that we detected in this data set under optimal management was non-crossover GBE, scaled GBE. This explains that the genetic variances within these 5 mega environments were quite different or could be quite different, but at the same time we have really high genetic correlations, as we saw. And again, the G/E interaction that we would discover here might be high, but it might not be harmful, and it might not justify a subdivision into different environments. And yeah, as I gave my acknowledgements at the beginning, that's it, and looking forward to get your questions.
Thank you, Christian. I think that was a pretty good example of the methodology. Thanks for taking the time to put it together. So let's go to the discussion. I extended the meeting for another 30 minutes. I hope some of you can make it. I know some of you have to leave, but I think this is a time to make questions or comments if you have some. I know that some of you have work in similar topics, the TPE definition, or even exactly this analysis in other crops. So please feel free to jump in, especially, I mean, if you were keeping some questions from Gary as well. So please go ahead. Let's start. I know some programs are exactly working on this, like the potato program, the bananas. I mean, there is many crops that want to define their TPEs, and the ones that have already defined them, they want to also delineate this better. So I think also Vivek and Joseph are around. So I don't know if you have any comment on the data. So please feel free to jump in. Please, Joseph, go ahead. Oh.
Okay. Thanks, Eduardo. Thanks, Gary and Christian. So my question is for Christian in terms of just to see the data source used. So is this the same material which is evaluated across the 5 mega environment? Because I thought at least for some of mega environment, the hybrids, which is different by maturity for dry lowland and wet lowland. Those maturity is different. So just I want to know from you, is it the same hybrid which is evaluated across those 5 mega environment, or there are different sets of trials?
That's a good question. Christian, yeah, let's go ahead.
Thanks for your question. I'm not sure if this is the answer that that you're asked for. Here we go. Otherwise, maybe Gary, you might know more, jump in, or maybe if Jill's around. So we had a set of 227 maize hybrids which were tested or which were represented in the whole data set in all 5 mega environments. And these are the numbers of hybrids which were tested within the single environment. So you can see if this, again, is the question you had, that most of the maize hybrids were tested in all environments, at least 184.
It's the CIMMYT regional trials, Joseph.
Yeah, Gary, I just, my question is it that, for example, there is early and then intermediate late, at least 2 group of categories in that regional trials. So the whole hybrid is together, or only just one of either the early or intermediate and late?
I had no information in the data set that I received on maturity.
Okay. Yeah.
Okay.
Yeah, I don't think it was part of the columns, but that's a good point. Something to also take a look, indeed.
Yeah, the earlier example was separately done for maturity, for the early versus the medium maturity set. Jill, do you recall from that data set if it was one or both maturity groups?
I don't think Jill
she may not be
today. Yeah, she didn't connect it today. But yeah, something to take a look.
I think it was one, but yeah.
Okay.
Yeah, thanks, Joseph. Good point. Hopefully, I mean, because it's
just on that, you would expect if it consisted of both maturity groups, you would expect to see more G by E.
Yeah.
Than you did. So my guess is that it was one set.
Yep. Good. Let me move to Ravi, because there's many people now with a question. Please, Ravi, go ahead.
Yeah, thanks for the nice presentations, Gary and Christian. So Gary, you in your talk you mentioned about Obregon. Thanks for doing that, because that's an interesting case where you had very nicely managed selection environments. And then you could still, using that data, can target your breeding lines to different TPEs. And the analysis which was done for wheat shows very similar to what Christian was showing and concluding, if I got it right, that the response to selection in your managed environment, if you do that well, in maize it shows for Africa was much higher than going and making many trials in the TPEs. So I think maybe that was the reason why in the wheat having a good research station with good consistent management condition has been giving us good progress, and not just for South Asian TPEs, but if you want to call TPEs or mega environment for many other countries. So this also brings the issue of strengthening in each center or each national program, how they do the testing, and we need possibly to, if you want to make faster genetic progress, start to invest in those testing sites. So that was my observation.
Yeah, no, good comment, Ravi. Gary, you want to say something, or that's okay?
Yeah, in the maize example, that example, the maize program is organized differently. It does a lot more multi-location testing earlier. So it doesn't do all of its testing at one location. It does it initially, and I think in stage, Joseph or Cosmos could comment, but initially at 3 or 4 locations, and later, even starting at stage 2 at many locations within the TPE. Different strategy also generates very good response. The question is what strategy will generate the best response, and that there's no one right answer, but it's important for us to provide the data to justify the design decisions that we're making.
Yeah, that's a good point, and I think those are valid comments, Ravi. I think the important part is to generate the data to make sure that we're taking the right decision. Great, thanks. Ganga, do you want to make your comment or question?
Okay, thank you, Eduardo. My clarification I would like to hear from Gary. Gary, you know me, I'm in Nairobi. Before coming to ICRISAT, I was wheat breeder in India. And most of the lines we are getting from CIMET, they were very much adapted to South Asian conditions. And there are several examples of Attila, PBW 343. All those things came from CIMET testing in Mexico. I don't know what was the reason, but somehow they are highly adaptable, even though they were selected outside the TPE. Just I wanted to get your ideas, what might be the reason. Even early varieties like IR8, IR64, they were performed very well in several countries. Maybe some commonality with respect to altitude, latitude, maybe other factors. Can you throw some light around there?
Sure, I can give my opinion, and Ravi his. Basically, the Mexican and South Asian TPEs are both irrigated dry season in the case of South Asia environments, and so they're really sort of yield potential screening, which works very well at Obregon for irrigated target environments in similar types of latitude. Absolutely works well. probably a little less well for rain-fed production in Ethiopia, where you've got more rainfall variability, longer cooler seasons. The Erie case, Erie did a lot of, had a lot of success with the Green Revolution irrigated varieties through about IR64 in South Asia. IR64 was released in 1985. It didn't have a lot of impact in South Asia on irrigated production after that time. And it was probably because the basic product out of that program was, developing and then adjusting semi-dwarf rice for irrigated systems. And once the plant type was changed, the quality was sort of reached a really good level in IR64 and the disease resistance spectrum. For a number of reasons, they didn't make a lot of progress for about 20 years after. And so you find relatively little impact of until more recently, and mainly out of the rain-fed program, which does a lot more testing in the TPE for the Erie irrigated program. But yes, obviously Obregon is a really good analog and predictor for Indian irrigated production environments. It may be not quite as good an analog for highland East Africa, which is one of its other major targets. Ravi may have a comment.
Yeah, Ravi, do you want to make your comment?
Yes, so Gary, maybe first part you said is correct. The other part is also partially maybe correct, but if you see the analysis on genetic progress in semi-arid environments, you would say all highlands, you will see very similar genetic gain from all the analysis and the adoption of varieties going from Mexico. So I think yield is the driving force, whether you take under irrigated or in Obregon, the benefit we have is the lack of rain. So you could have good data on performance under drought as well, the same years side by side. So that probably helps. And then the part here in Mexico is the alternative site where the materials are selected is an highland site, which
That's true.
is not
That's
that
true.
different from Ethiopian highlands, except one disease maybe. The stem rust there, which we don't have that race here. So other than that, if you take septoria, yellow rust, the same high rainfall or drought, depending on the year, it could be very similar. So maybe that has given the edge of selection in Mexico, and it's still lines which are being released by countries and regions, whether you have drought or whether you have high production conditions or different diseases. So it's a packaging, it has been important.
There's no doubt that that selection is working very well. It doesn't follow, however, that you might not get greater gains if you did more selection in the TPE, applied more selection pressure in the TPE. It's quite possible that you could increase the gains. So that's a hypothesis that's worth looking at.
Yeah, thanks for saying, Gary, because that means, as I initially mentioned, a lot of investment was made to improve the testing environment or selection environment. So if we go out to, let's say, Ethiopia, we need to make investment to match up. Otherwise,
Exactly.
response to selection might not be the same. And,
yeah.
And this is another big issue which needs to be looked if we start to move into TPEs. Thanks.
Yeah, thanks, Ravi.
Yeah, thank you, Ravi and Gary, for that clarification. Thank you very much.
Thanks, Ganga. Bauja?
Thank you.
Yeah, we can hear you now.
Very, very nice presentation. I think this is very important. And do you hear me now?
Yeah, I think there is some connection issues, but
thank
yeah,
you so much for this nice presentation. Yeah, no, it's now internet is not so good. My comment is very similar to what Robbie mentioned before. You know, I was shocked to see these results because Africa is very diverse, okay, and then it's a lot of variation there, but it's indirect selection is working very well with permission. One question I have is about the quality of the trials. How those some location and some sub regions, the repeatability was a bit lower, maybe because of trial management. But overall, it looked like you know, the question is about the resource allocation, and now, as Robbie mentioned, we have moving towards different direction in wheat, and then now I think it's the right time to think about how to allocate resources, and then not overwhelmingly dividing these the mega environment into different small TPEs maybe. So I think this is very nice study, and I would like to have more conversation with Christian as well. Yeah. And we have very similar data in wheat, and then we have, you know, I would love to move forward with similar analysis as well.
Yeah, Christian, Gary, do you want to comment on Boja's question on the quality of the trials that was used for the analysis, the high generic correlations, and the resource allocation that the WheAT program needs to start doing?
Gary, you want to go first?
Oh, I think Boja's was more of a comment than a question, but yeah, you know, it's quite important that individual trials have reasonable levels of heritability, and if they have zero heritability, they should be rule I would follow for whether a trial should be included in a combined analysis or not is, does it increase the heritability of the mean? Central revolves around that are, you know, directly managed by CG programs, revolves around the you know, you'll hear CG breeders say, well, our partners, they can't do good trials. We don't get good data back from our partners. This comes back to Ravi's point about having to invest in facilities with partners. Part of our responsibility is to make sure that our partners can do good yield testing. So, you know, part of the responsibility of a CG breeding network is to work with partners to help them improve the quality of their trials.
Thanks, Gary. Yeah, Christian, you want to say something? Or?
Yeah, just might comment on the high genetic correlations again, and I mean, we were also surprised that that we observed these high genetic correlations. Although you would assume that different regions across almost the whole African continent are quite different in their conditions. I think again it's again important to point out here we only looked at the optimal management, and all the experiments, all the trials with drought stress were removed, which is certainly an important factor. Some locations were irrigated, which is probably not very common among farmers. So I'm probably not too surprised that the optimal management genetic correlations are that similar. The very important question here is probably, are these optimally managed experiments representative for the farmers? And Gary made that very important point at the beginning, that the locations that are not used by the farmers certainly are your experimental sites. So I guess I wouldn't draw conclusions from these results that I showed without further discussion with the breeding teams. But I guess the major reason here is it was only the optimal management, and we excluded all other factors just for illustration purposes.
Can I just make a quick add-on to that? The previous analysis that Vanessa did on the 2001 to 2009 data showed very similar results. And the one major source of sort of predictable G by E that would, lead you to divide the TPE for maize in Eastern and Southern Africa was yield level of the trials. So trials that there was a big re-ranking for trials that yielded under 3 tons per hectare versus trials that yielded over 3 tons per hectare. And most farmers in sub-Saharan Africa, get substantially less than 3 tons per hectare. So there's really a sort of optimal versus suboptimal environmental interaction that for maize in Africa and for a number of crops you would need to consider. In South, the big difference between African agriculture and South Asian agriculture is in the access farmers have to fertilizer and irrigation, but particularly fertilizer. So farmers in South Asia use about, in cereal production, about 4 times the level of, on average, fertilizer that sub-Saharan African farmers use. And so conditions on research stations tend to be much more similar to conditions on farms in South Asia than they are in sub-Saharan Africa. We just finished a big analysis of on-farm versus on-station trials of the Bangladesh Rice Research Institute. They have a massive on-farm testing program. They test on-farm, about 300 locations a season. And the genetic correlation between on-farm testing for this relatively high input, well-managed production system farmers have in Bangladesh for rice, average yields are well over 4 tons per hectare. The genetic correlation is about 0.9. And in fact, the repeatability on farm was higher than on the research station, the heritability. So the conditions in sub-Saharan Africa that farmers face are really different, generally speaking, than in South Asia. And you probably need a different approach to testing.
Can I ask Hans to contribute, because I think he raised his hand based on your comment. Is that correct, Hans?
I had a actually question I want to ask to Gary, if that's okay.
Okay, yeah, let's go for it. Sorry to Medina and Willa too. Yeah, please go ahead, Hans.
So Gary, I was wondering and going to ask you, how comfortable do you feel with some of the work we have been doing with the EIB and even other centers on market segmentation, which are primarily based on various factors or elements, of course, depending upon the crop and the region you're talking about. And not much analysis or these kind of analytics have been applied to come up with those market segments. So how comfortable you feel that is it a right approach, or are we missing something big there?
I think you need both. I think breeding programs have to identify the type of product they want to deliver in terms of quality, what a particular market requires. And they have to identify a group of farmers that they want to serve, a production system that has the maximum potential to improve livelihoods and alleviate poverty in the case of a CG breeding program or a NARS breeding program. So that market segment, defining the market segment is the first step. Within that market segment, there may be biological reasons to break up into different breeding pipelines. And that's what these analyses serve. So, you know, this type of G by E based analysis, heritability based analysis in terms of selection response, you do that once you've identified, I think, a market segment that you would want to work on, not after.
Or the other way
before, I should
around,
say.
Gary?
Yeah.
Instead of breaking out more, consolidate more than one market segment, or how do you
Well,
see that?
no, I mean, you know, if the market segment requires, say, low, you know, sticky rice versus firm rice, you know, you need two pipelines, right?
Yeah.
So it's the market segment is first. Then, but within the sticky rice, for example, pipeline, you may need a specific pipeline for the wet season in Laos and Thailand versus dry season irrigated in Laos and Thailand. You know, that's that at that point you may need to do this analysis and determine whether you would be better served by two pipelines.
Yeah, but I understand the concern from Hans, because it depends on how much we partition what a market segment is, right? Because if we actually put too many variables, not only, let's say, the quality or the type of grain, but if you put on top of that, okay, also a market segment implies this type of, you know, shape, color, region, etc. You partition it so much that at some point, then it makes the question how many market segments you can cover with one pipeline. But I agree. I mean, if we keep the market segments at high level, then it's easier that then you do this G by E analysis.
Yeah. But I mean, the CG's been brilliant at identifying major market segments that serve immense areas, right? So the main, you know, the main wheat product profile in terms of quality that the CIMMYT wheat program serves is acceptable, you know, on tens of millions of hectares globally, right? There are, and those are the market segments that the CG has to serve. Same with rice, you know, slender grained, sort of medium soft rice that the IR64 quality grade was acceptable across millions and millions of hectares. So that, and then smaller niches, you know, you have to make a decision on probably the, you support national partners to serve those niches.
Yeah, very common.
So Eduardo and Gary, you know, I think in the industry there are many examples where breeders or a particular breeding program has been breeding for what you call the mega environment or breeding zones. But when it comes to testing and selecting and positioning specific products, then that's where you go to these smaller pieces or smaller segments, which are very specific. And that's where you apply all these different parameters or factors, whether it's a grain quality or is a particular other trait of interest. So I think this is another thing which we need to be thinking about, particularly in the CG system. And when we are building breeding programs or what we're calling as the breeding pipelines, we need to make sure that they are big enough in scope. We can't be really coming down to such a narrow specific thing. Then I think that might not be the best use of our resources. Absolutely.
And so basically the argument here is that what Christian showed was you don't need to break up the CIMMYT pipeline into those mega environment splits, right? It's not necessary. So generally speaking, human researchers, I think, tend to split up environments more than plants do. Plants can't run away from the environment. So they tend to be very broadly, they tend to be broadly adapted. And our testing systems over years really select for broad adaptation because, conditions vary so much from year to year. Sorry.
But then going to the comment from Hans, then a program that actually has divided their pipelines based on mega environments is not necessarily the best way to proceed. So first you think on quality, the market, etc. And as you mentioned, then you see if you should split by mega environments, not the other way around.
Sorry, I'm not sure I caught that, but I would say, yeah. generally speaking, if you have very clear market requirements for quality that are, broadly acceptable across a region, you start with that, and then there may be, production or environmental differences within that region that requires, for example, there's a very broad, from the world that Hans used to work in, a really broad product profile for maize in North America in terms of quality, but some areas need short duration and some areas need long duration hybrids.
No, yeah, it was just a warning that if some programs are thinking on splitting their programs just because of the TPE without having this type of
That's right.
analysis,
Generally
might
speaking, you
not be
don't.
a good
Sorry.
idea, as you mentioned.
Yep.
Yeah. No. That was it. Mhm. Do we have a last comment from Madina? Madina, do you want to jump in before we close?
Yes, thank you. I'm following a question that I'm just reading. That's my first question. So the person is Sikiru. He said, if the environmental variables data is available for the period of analysis, it will be good to include that instead of taking them as estimated effects. So my question is, that was my question, how do we include those major environmental variables if we have them for the period of analysis? So
Christian, you want to say something?
Yeah, good question. I guess unfortunately there's no easy answer to that because modeling always depends on your assumptions. So let's assume you have a major environmental component that might define another target population of environments. So in that case, you could just follow the same approach and say, okay, we're splitting our environments not by location, but maybe by drought or something like that, by rainfall. And then you could compare if this has a major effect on genetic gain and if you should keep these environmental defined locations together or not. If it is just something that happens that you assume happens within an environment, you might, depending on what it is, just include it as a fixed factor. If it's, I don't know, maybe fertilizer. If it's rainfall, you might include it as a random factor. If you just include it as a factor to correct for, you can compare different models and check how well they reduce your error. What is their log likelihood? Things like that your biometrician should be able to do. My assumption then would be the factor analytic models tend to capture a lot of that hidden environmental factors. And Eduardo and I, we ran a lot of different models with a couple of terms included, a couple of terms excluded, more parsimonious. We compared factor analytic to others. What we observed was, of course, the numbers change, but the basic take-home message, the results stayed relatively similar. So I don't know, that probably wasn't a very satisfactory answer, but there is no easy answer to that. But very often sometimes we tend to overestimate the importance of these factors, but your modeling will tell you, and your biometrician should be able to see that. But maybe, yeah. Eduardo, you want to add something?
Maybe just that, I mean, if you have access to that type of information, Madina, I think you can always just kind of remove the issue that some of these variables just say location X, location Y, or mega environment X and mega environment Y, and put a name into those variables, like is it temperature, is it rain? And I guess, as Christian was mentioning, you can always design some analysis to test a hypothesis and put a name on what is driving the genetic correlations. Is the genetic correlation being driven by the amount of water, by the temperature at this time, at that flowering time, or something like that? There's always interesting things that you could do if you have access to that information. But yeah, I think there's so many that I will not say that there is a state of the art or specific analysis that I would recommend now. Let's sorry, Martina, that I cannot expand. That we have to finish the meeting because many of us have a meeting just right after this one, and we only have 1 minute. I want to thank everyone for the comments and questions. Really, that you were willing to participate much more than in previous sessions. Thanks to Gary and Christian for the great presentations. I think that actually made that most of the people stay for another 30 minutes. And have a great day, and we're gonna meet you in a month for the next presentation. Hopefully you can join. Thanks again.
Thank you.
Thank you.
Thanks, everyone. Thank you.
Thank you, everyone.
Bye.
Thanks.
Bye.
Okay, thank you. Bye-bye.
Bye, everyone. Bye.
Take care.